this one is closed at one end, this air column, but the same basic method will work. Based off the name of it, this one's the second resonance, and based off the fact that it's closed at one end, I can draw what the standing wave would look like. Sound is a longitudinal wave, but I'm going to draw it as transverse to help me visualize it. And the rule is draw a node at the closed end and an antinode at the open end. This one's closed at one end, so I'm going to draw it starting with a node. It ends in an antinode. If it said the first resonance, that's what the standing wave would look like. I've drawn half a football shape, so that's half of a half, so that's a quarter of a wavelength. But it said second resonance, so I need to go into the next antinode. So swoop down to there, swoop up to there. That's actually a pretty good drawing. That's what the standing wave pattern for the second resonance, that's how we're going to model it, that's how we're going to draw it. That's not quite a full wavelength. I've got the football shape and then half a football. So really what I've got is 3/4 of a wavelength are fitting into the length of the column. The numbers I made up, 3/4 of a wavelength is fitting into 0.3 meters. Flip-flop things around and clean that up. It's kind of a clean number. Ends up being 0.4 meters as the wavelength. If we cared about wavelengths of sound, we'd be done. But in sound, we often care about the frequency. We can get frequency from our universal wave equation. From now on, whenever we see a temperature in disguise, that's really telling us the speed of sound. Speed of sound is always 332 plus 0.59 times temperature. So for the numbers made up this time, that's 332 plus 0.59 of 20, which I'm getting as 343.8. To finish it off, the wave equation connects those two. V is equal to F times lambda. Frequency is going to be V over lambda, in this case the 343.8 number divided by 0.4. We end up with the meters canceling. We're getting a number in per second. A per second is the same as a hertz. I've rounded it off a little bit, but I'm getting 860 hertz. That's what sound you would hear from the second resonance, closed at one end, in 20 degrees Celsius air.